don't even remember. I guess it was one.
No, you can't sit there.
I guess back
You gotta sit out in Miss Klukas' office. Oh, you can sit wherever you want. As long as it's not too close to me.
I do too. I literally have Virginia and BYU winning losing first round.
Did someone change class time or what happened?
I don't know. It's been walking around for like 500. Oh yeah, that's what I mean. I was gonna wait for other people to throw it out. I'll yell at you. He has literally no idea. Hey, I'm saying you were $5.
All right.
How many teams do you win out of the tournament? How many teams do you win there in the tournament? Yeah.
No, 66.
No, like how many teams like you actually win? There are
68, come on.
32.
Oh. All right. Oh,
It's 60.
68.
Two.
Because they have two on the
Oh.
it's technically 72 because there are 4 waiting in the wings just in case, right? All right. So, approximate integration. We've already talked about different ways to approximate integrals. We talked about using rectangles, measuring from the left-hand side of the subinterval, the right-hand side of the subinterval, and we've talked about measuring from the middle of each subinterval. We're going to introduce 2 new methods today. Both are a little more accurate. One of them is immensely more accurate. And only one of the 2 is actually on the AP exam, okay? But they're both good to know. So why would we still need to worry about approximating integrals? 2 situations that could arise. One, if we have a function that we don't know the antiderivative for. We can't integrate it. The other, and more common, see it on the AP test all the time, if we're just given data and not an explicit function, we can use these approximating techniques to estimate the integral or the antiderivative. Bring one for me.
It's not very COVID friendly, right? Come on.
Why do you just
Yeah, I don't know. Just do anything that doesn't make as much noise as possible. I've already done that.
All right. So there we go. Some possible solutions for approximating area underneath the curve. Midpoint rule we've used. This should be kind of old news stuff. And so you're just taking your delta x, which is calculated the same way we've calculated delta x since 5.2 times our f of x sub 1 actually should probably be well, f of x sub 1 plus f of x sub 2 all the way up to f of x sub n, where each of these x sub values are calculated the same way. You take the left endpoint of a subinterval plus the right endpoint of a subinterval and divide by 2. There are actually easier ways of calculating those, but we'll talk about those later.
Sorry.
All right. The more accurate or a more accurate approximation comes from what is called the trapezoidal rule. And it's called the trapezoidal rule for a very good reason. I will show you that in a minute. But the trapezoidal rule, you take delta x divided by 2 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2, all the way out 2 times f of x sub n minus 1, so your second to last x value, and then plus f of x sub n. Our delta x is still calculated b minus a divided by n. And our x sub I, so this x sub 2 would be a, our lower limit, plus 2 times delta x. If we were finding the fifth, actually x sub 5, we would do a plus 5 times delta x, and so on. It's called the trapezoidal rule because basically, instead of areas of rectangles, we're now finding areas of trapezoids. On the AP exam, you may also see this referred to as the trapezium method. That's probably a scholarly word that I just don't know of. Yes, sir.
What's supposed to go like between the first x? See those parentheses there? How there's x sub 1, sub 2, and then halfway through the equation.
Yeah.
Put x to the parentheses instead of like a 1 or 2, the sub numbers.
Here?
No, up to the right. The right. Right there.
So okay, I'll show you. All right.
Like, see, there's no like 1 or 2 in there. Is that a 0?
That's a 0. That's a 0. Yeah. So basically, what we're doing here, if we have a function I don't know, that's going to be my f of x. And maybe a is here and b is here. And so a is also our x sub 0, my x sub 1. Over here maybe it's my x sub 2. So what we're looking at is a trapezoid where the height of the trapezoid is our delta x. And f of a is one base, f of x sub 1 is the second base for this first trapezoid. For my second trapezoid, and it's going to look really weird, we would have, actually that's not, it's difficult to draw. It's actually like this, where x sub 1 is a base, x sub 2 is a base, and I put it as x squared for some reason. That's really not good. There we go. And the height again is our delta x. Okay, so for the first trapezoid, the area, remember, area formula is 1/2 base 1 plus base 2 times the height, and the height is our delta x. The second trapezoid, 1/2 base 1, which is x sub 1, plus base 2 times the height, and so on. Well, we can factor out anything common, so we can factor out that delta x and the 1/2. So that's why we have delta x over 2 in the beginning of our formula. And then we would multiply that x0 plus x1 plus x1 plus x2 plus all the way out. That's why our middle terms, we take 2 times, I'm sorry, these should be f of x. Really neatly drawing those in. And so that's why in the middle of our formula, we have 2 times f of x sub 1, 2 times f of x sub 2, all the way up. The only function values that are not doubled are the first, so f of x sub 0, and the last, because those will only be bases for one trapezoid. Everything else is a base for 2, the one on its left and the one on its right. Sorry for that. It's Wednesday. I shouldn't be teaching today, right? That's normally our day not to have. That's what I'm going to blame it on anyway. But it'll be nice Friday, right? You guys don't have to wake up early. All right. So we're going to do a trapezoidal rule and a midpoint rule with n equals 5 to approximate the area under the graph of the integral from 1 to 2 of 1 over x dx. And then we're actually going to compare that to the actual, because we can take that integral, right? What's the integral of 1 over x? What's the integral of 1 over x? Natural log of x. Yep. So we can compare our approximation with an actual value. So if I calculate my delta x, lower limit minus upper limit divided by n, my delta x would be 1/5. So for our trapezoidal rule, with 5 subintervals, we're going to take our delta x divided by 2 We're going from 1 to 2. So I'm going to have my function value at 1 plus 2 times my function value at 1 plus delta x. Our delta x is 1/5 or 0.2. Plus 2 times f at 1.4 plus 2 times f at 1.6 plus 2 times f at 1.8, and then just f of 2. Excuse me. So personally, I would do this on my calculator and use my lists. So if I go to my calculator, and I would put my x values in L1. So it was 1, 1.2, 1.4, 1.6, 1.8, and 2. In L2, what I'm going to do a little bit different, I'm going to put the number that I'm multiplying my function value by. So I multiply by 1, 2, not 22, 2, 2, 2, 1. And then in my third list, I'm going to take my L2 value times my function. My function was 1 over x. In this case, my x values are in L1. I could also just do L2 divided by L1. That would work. All right. So then my integral is going to be my delta x 1/5 divided by 2 times, and if I do second stat math, I can then take the sum of L3, which is where all of my values were. And there's my approximation using the trapezoidal rule. How close is that approximation? Well, we said 1 over x, the integral of 1 over x is ln. So that would be the ln of 2 minus the ln of, well, what's the ln of 1? 0, right? So I actually wouldn't have even needed to put that in, but so here is the actual integral, and here's our approximation using the trapezoidal rule. Again, round to 3 decimal places unless you're told otherwise. So 0.696 for our approximation with the trapezoidal rule. Is it empty? There's one right on the table there, or on the, yep. We have hand sanitizer just about anywhere. All right, so there's using the trapezoidal rule. midpoint rule, which was the other thing we were asked to do. Formula's a little more simple, a little easier. It's just our delta x times our function value at the midpoint between 1 and 1.2. So what's halfway between 1 and 1.2? 1.1. And now to find my next function value, I'm just going to add delta x to my previous x. So x was 1.1. I'm going to add a 1/5 or a 0.2 to give me 1.3, 1.5, 1.7, 1.9. Sorry, that's me. Yeah, that's not a good warning. So again, you could use your lists in your calculator to calculate this. I'll just do it on the main screen to find my approximation. So my delta x 1/5 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And you can see we have 0.692 as our approximation. So trapezoidal rule, kind of new. Midpoint, one that we've used in the past. So here comes the more accurate and, of course, more complicated approximation method called Simpson's rule. Has nothing to do with jelly donuts, so don't get excited. All right. Simpson's rule. So for Simpson's rule, to approximate the integral from a to b of f of x dx, we're going to take our delta x divided by 3 times our function at x sub 0 plus 4 times our function at x sub 1 plus 2 times our function at x sub 2 plus 4 times our function at x sub 3. And it alternates that 2, 4, 2, 4, 2, 4 until we get to our 2 times f of x sub n minus 2. So our third to last function value plus 4 times our function at x sub n plus 1 or n minus 1. So that's our second to last function value. And then plus our function at our last x value, x sub n. In order for Simpson's rule to work, n has to be even. So we couldn't do 5 subintervals like we did with the last couple of approximations. It has to be even. Our delta x is still calculated the same way. B minus a over n. if n is not even, this alternating 4, 2, 4, 2, 4, 2, ending with 4 and then 1 wouldn't work. This one is not, you won't see it on the AP exam. Trapezoidal rule you'll see. Left and right endpoints you'll see. Again, I just want to show you this because it is immensely more accurate than any of the other methods we've used. All right, so here we go. Use Simpson's rule with n equals 10 to approximate the integral from 1 to 2 of 1 over x dx. So we're using twice as many subintervals as we did for the other one. So that's going to make it more accurate already. But we're using Simpson's rule, which is going to make it even more accurate. No, even more accurate than more accurate, no, more accurate than those other approximations. So our delta x, b minus a over n. So Simpson's rule with 10 subintervals. 10 is even, so that's good. We can use Simpson's rule then. Delta x over 3. We're going to have f of 1 plus 4 times f of 1.1 plus 2 times f of 1.2 plus 4 times f of 1.3. And I'm going to quit writing those for a while. It would end at 2 times f of 1.8 plus 4 times f at 1.9 plus f of 2. Again, I would probably use the lists on my calculator. And I'm going to show you a little trick that you can use when you're doing both Simpson's and the trapezoidal rule. Because both of them will use one more calculation than the midpoint rule will. Okay. So what you can do on your calculator if you go to your lists and so I'm clear these out for now. If I was going to do trapezoidal and Simpson's for n equals 10, I'd put in my values from 1 to 2, counting by 1/10. If I was doing trapezoidal, I would do 1 and then a bunch of 2s and end with a 1. With Simpson's, 4, 2, 4, 2, 4, 2. So you can easily manipulate L2 to fit either Simpsons or trapezoidal, as long as you have the same number of subintervals, which on your homework you will. And then here, I'm going to put in parentheses my function times my L2. So I'm going to take L2 times, and my function in this case was 1 divided by the values that are in L1. And by using the quotes, it's going to remember that function. So I'll show you, I can now calculate Simpson's rule, but I can also do the trapezoidal rule pretty quickly. And so for Simpson's rule, it's my delta x divided by 3 times the sum. So go second stat over to math, option 5. Make sure we do L3. So here's the actual, and here's my Simpson's rule approximation. So a little bit more accurate than, okay, a lot more accurate than the other ones. 0.693 as opposed to the other approximations. So I said that we could do trapezoidal pretty easy with that setup. And the way we would do that, we just go back into our list and we could just change everywhere there's a 4, I would just change it to a 2. And because I put the quotes in, it's changing my L3 as well. And so just something to keep in mind as you're working on your homework. It doesn't work well with midpoint because there's one less value when you do a midpoint approximation, okay? So personally, I would do the midpoint on the home screen of the calculator and use trapezoidal and Simpsons both in the lists. That's just that's what I would do. You don't have to do what Mr. Gingrich would do, but that's, again, can save a little bit of time doing it that way. All right. So this one. Again, AP exam round to 3 decimal places, which I think I commented on your last test. Make sure you round to 3 decimal places, just to reinforce that. I would reinforce that all the time, and I just forgot. So I didn't take points off. That wasn't a big deal. So your assignment, twofold. You've got your regular assignment on midpoint, trapezoidal, and Simpson's rule. And then a review assignment on Tuesday for this group. I will push out an AP problem. On Monday. Sorry, Monday, and the in-class group will be taking the test on Monday. So I'll answer questions and go over all of that. And then on Wednesday, they will get that AP problem. They'll have access to it before that, but and then you guys will quiz test on Wednesday in person. I know it's kind of disappointing, no homework over spring break, but that AP problem won't be due until like Friday next week. So I'd rather have you, and it will be pertaining to stuff that we've done in chapter 5. So. And so you've got, plenty of time to work, almost an hour. So.